Today we're going to talk about volumes. So let's first introduce the idea. Let's say we're given this shape, the picture, you notice this given shape, and they ask you to find out this volume. What you need to do is, what basically we're going to do is we try to approximate it again. Approximation by cutting through this curve. So if we cut through this, you'll notice you'll have this cross section. So those cross sections, if you break it into like 20 pieces, look at this case. If you divide it into 30 pieces, this is what we get. If you divide it into more slices, the number of slices that you use and calculate each volume separately, then the more accurate the approximation becomes. And similar to what we did for the areas, you add up all those, and we can notice that they have a similar idea as the integral that we defined for the area under the curve. So for the volume, what we need to do is basically calculate each of these cross sections, call it the area in each cross section, and add up all those cross sections. Basically, you find the function of those area and you integrate it. Integrate from the beginning to end for a variable x. So if you start x from, let's say x starts from a to b, you integrate all those volumes from x changing from a to b, and the volumes are correspond to each cross sections. So normally what we try to do is we find the area for each variable, for the variable x, where x changes from a to b, we find the area as a function of x. If you pick the variable to be along the y-axis, then the function to be a of y. Okay, so this makes more sense through going through an example. So here, let's see the sphere. We want to find the volume of a sphere. So first, I'm going to draw a sphere. It's kind of hard to imagine. So let's say you have a 3-dimension. Actually, let me just use 2 axes, x and y, so it's not confusing. And I'm only going to focus on the quarter of a circle, quarter of the sphere, because it's symmetric. So what you notice is something like this you'll have as the sphere. Okay. Yeah, well, you might ask yourself, this is not a sphere. So let's say this is a sphere. I'm cutting through only this piece, this right hand. You can pick up a ball and look at through that. This would be only a quarter of that sphere. Okay, so there's no axis along the other side. So it's just for you to notice. I don't want to add this axis. This is called the x, y, and z axis. I don't want to do that. I'm going to say, let's say stick with x and y. Okay, so if we cut through, x changes from 0 to the radius of the sphere. Let's call it capital R. So let's call this length to be capital R. So if we cut through a section of this sphere, so if I cut through here, what you notice is this area is basically a circle. These two are the same thing. If you look at it through this direction, you will see a circle. In 3D, it's kind of difficult to see. But here in our curve, I've only focused on the upper half. So what do I have is, this is only the upper half of the circle. With the radius, let's say this is the radius. The radius is given r, and we don't know what that radius is. We just need to figure out the radius. So let's assume that x is here. X is a variable changing between 0 to r. So what we have is this triangle with the length x. This capital length here is the same as the radius of the sphere. So this is r. And we want to find out the small radius, the radius of the small circle, this cross section. So basically what do I need is this radius. you need to be good at seeing the curve, because it's not that clear that this is a upper half of the circle. But if you cut through the sphere, you'll notice that this is basically a circle, which means I need to figure out the radius of that circle and figure out the area. So we want to find out what is a of x. That's what we're looking for. So we can replace it in the formula and say, okay, I want to integrate from 0 to r of a of x. This will give me the volume. So by doing so, I just need to figure out the area. And what is the area of a circle? It is pi r squared. Again, I'm looking for this cross section, the upper half. Since it's the upper half, it would be 1/2 of pi r squared. And what is the small r? The small r, using the Pythagorean identity, you can say, okay, small r is capital R squared minus x squared, take a square root. This is Pythagorean identity. X squared plus small r squared would be capital R squared. Then move stuff around, you can figure out r, small r by doing that. So what would be the area? It would be 1/2 pi r squared minus x squared. The square root and the squared will cancel out. Instead of r, I replaced capital R squared minus x squared. So what would be the volume? The volume would be integral from 0 to r of ax. Ax is 1/2 pi r squared minus x squared dx. Capital R is a fixed number, so you will get 1/2 pi. The antiderivative would be r squared. The antiderivative of r squared is, since it's a constant, it would be r squared x. The antiderivative of x squared would be x cubed over 3. Evaluated from 0 to r. The good thing is, by replacing 0, we get 0, so we just need to replace r. So you get 1/2 pi r squared times r would be r cubed minus r cubed over 3. And that simplifies to 1/2 pi times 2/3 r cubed. Okay, so we found out the volume, which is 1/3, these two will cancel out. 1/3 pi r cubed. But this volume is not for the whole sphere. If you remember, we started with the quarter of the sphere, and this quarter will give us 1/3 pi r cubed. So what would be the volume of the sphere? It would be, if you multiply this by 4, 4/3 pi r cubed. This is the volume of the sphere. And normally you're given this formula, but now you can prove it, that basically the volume of a sphere is 4/3 pi r cubed. Okay, so one thing that is important is to figure out this cross section, this area. If you figure out that, it's just integration after that. Here's more example. Find the volume of a solid obtained by rotating about the x-axis. So here, what it means is you're given this square root of x function. This is how square root of x looks like, from 0 to 1, 0 to 1, and square root of x. And they say, rotate this about the x-axis. What you get is this kind of cone shape. And they say, find out the volume by rotation. The volume of this curve, this area under. If you rotate this area under, what you get is the volume. Again, I know that x is a variable between 0 to 1. So let's pick x to be somewhere here. And if we rotate, we look at the cross section here. What you have here is a circle. It's kind of hard to imagine, but if you look at through this direction, you should have a circle because you rotated this curve. The distance always was a fixed number. This should be a circle. from 0 to top, this would be this upper half of the circle. You'll have this circle. You will notice this might be the circle. What is the height? The height is square root of x. This corresponds to the y value, which was square root of x. So what would be the area? The area would be pi r squared. In this case, the radius square root of x. So pi times square root of x squared, which is simply pi x. So what would be the volume? The volume would be the integral from 0 to 1 of the area ax dx. So the area is pi x dx, which would be pi x squared over 2 evaluated from 0 to 1. And that is pi times 1 over 2 minus 0, which would be 1/2 pi. This is basically the area, the volume obtained by this rotation. So you notice this is a positive number. You shouldn't expect the volume to be shouldn't expect the volume to be negative at all. And that's a kind of a check to make sure that the volume that you've calculated is positive number, similar to the area. Okay, it's not difficult as long as you figure out this cross-section area. If you find the area properly, then it shouldn't be difficult. Again, this area you can always draw the picture outside and expect a circle if you have dealing with rotation. Rotation always creates circle because let's say you have a fixed point. You have a fixed point as the center. If you rotate around that fixed point, what you create is always a circle. In this case, the x-axis is a fixed point. Correspond to that, if you rotate the curve, you always create this circle. So basically, the area would be 1/2 pi. Okay, here's another one. Find the volume of solid obtained by rotating about the y-axis. This time, what we rotate is the bounded region. Let me shift this up a bit. Okay. So what we have is these three curves, these three function. One is y equal to x cubed. This is y equal to x cubed. The other one is y equal to 8. Here's y equal to 8. And x equal to 0 is basically the x-axis. This is x equal to 0. And they say rotate this not about the y-axis, not about the x-axis, but about the y-axis. So what you get is similar shape to what we did in the last example, but the rotation creates this cone to be upward. So what is the variable in this case is, if you consider the cross section, say this is the variable in this case is y, because y changes from 0 to 8. Right, so we assume that the variable is y, so we can write the volume. Let me write this down here. Volume as a of y, the function of y as the area. And the volume should change, the y changes from 0 to 8. You can rotate this and put it on the x-axis and deal with it the other way as well. But I want to show you both directions. So if you change it to, if it's rotation about the y-axis, you assume that the y is the variable. So here, again, we cut through this and we have this cross-section. This cross-section is a circle where the radius, this radius is correspond to the x-coordinate. So this is x. So what is the area? Area would be, we want a of y. Remember, y is the variable. It would be pi x squared. But we want it in terms of y, since we have the area as a function of y. I'll say this is pi times, what is x? You're given this equation. Y equal to x cubed. So x would be cube root of y. You take a cube root from both sides. It would be, instead of x, I will replace cube root of y and squared. So what would be the volume? The volume would be from 0 to 8 pi cube root of y squared dy. Now the simple integration will calculate this. 0 to 8, I'm going to write it as pi y to the power 2/3 dy, and integrate. What would be the antiderivative? It would be pi y to the power 5/3 divided by 5/3, evaluated from 0 to 8. You can simplify it 3/5 pi y to the power 5/3. Y to the power 5/3 is cube root of y to the power 5. From 0 to 8. Again, if you replace 0, it will be 0, so you'll just need to replace 8. If you replace 8, you will get cube root 2 to the power 5/32. You can use the calculator to check 96/5 pi. And this is basically the volume of this cone, the solid, by rotating about the y-axis. So you notice that if I rotate about the x-axis, I write the function in terms of a of the cross-section in terms of a of x, and if I rotate about the y-axis, you write in terms of a of y. It's always optional. You can always rotate, you can always change the x and y-axis if you want. It's easier to deal with it this way. Let's look at another example. Here we have a solid, we have an area between these two curves, square root of x and x. And what we do is we rotate this about the x-axis. So let's see what we expect to get. Let's assume we have these two curves. One is square root of x. The other one is y equal to x. Okay, and they create this area between. And if you continue square root of x or y equal to x, there wouldn't be any region between these two anymore. So this is the only region bounded between these two functions. And they say rotate this about the x-axis. So if we rotate it, what you get is, sorry, it's not that clear. It's kind of hard to draw 3-dimension. So what you get is this kind of shape. It has an empty inside, and the outside is kind of this curve. There we go. Okay, so what this red line, actually maybe I should have used a different color. So this is the cross section. If we cut through this curve, what you notice is this kind of discish, where this would be empty inside and the outside would be, there would be a layer. So basically, if you look through this direction, what you notice is two circles and we want to find out this area and some integrate over all these areas. So what we have is two radiuses. One is this radius, the other one is the radius to the outer circle. What are those radiuses? We can figure them out easily. First, let's figure out these two intersection points, because you're having two curves. One is square root of x, the other one is x. From last section, we should know how to figure out the intersection point. Square root of x equal to x. We set up those two equal to each other. You can square both sides. You'll get x squared, x equals to x squared. Move x to the other side, x squared minus x equal to 0. Factor out an x minus 1 equal to 0. Therefore, x must be 0 and 1. These are the two solutions. That means the two intersection points happens at 0 and at 1. This corresponding x value is 1. And now, what is the radius? The radius for the outer circle is basically the height of the function. And the height of the function here is square root of x. For the other radius, this simply would be the height of the other function, which is x. So this would be the radius of the smaller circle, x. So what would be the area, this shaded area? The area would be pi r squared minus, it would be the difference of the two areas. One is the bigger circle minus the smaller circle. Pi square root of x squared, this is the radius of the bigger one, minus pi, the smaller circle squared, radius of the smaller circle squared. Pi r squared, x squared in this case. You can simplify this, they both have a pi in common. Factor out that one. Square root of x squared is x minus x squared. So this is basically the ax function. And you're going to find the volume, you integrate from 0 to 1, the boundaries from 0 to 1, these two. And pi x minus x squared. This is when you're dealing with a washer or a disk, or it's like a CD. The inside is empty, there would be a layer, you have to calculate the area of that layer. And that's always the difference of the two areas. Okay, so what we get is, find the integral pi, the antiderivative of x is x squared over 2. The antiderivative of x squared is x cubed over 3. And we integrate from 0 to 1. If you replace 1, we get pi times 1/2 minus 1/3, which is pi over 6. If you replace 0, you'll get 0. So this would be the volume created by this rotation. Okay, so this was a rotation about the x-axis. The same question, the same region, but instead of rotating about the x-axis, they ask you, what if you rotated about y equal to -1? This is a kind of a common question as well. So if you consider this, again, this is kind of difficult to draw, but I'll do my best to give you an idea. So this is the same region from 0 to 1. And now they say rotate this about the line y equal to -1. Here is -1. So if you rotate this about y equal to -1 is, let me rotate only a section of it. Here's what you get. This is the cross section. The curve will kind of look like this. And this is the cross section. What happened is the radius became larger. Compare these two. This one had the radius starting from the x-axis. The other one now has the radius to be this distance. And the outer radius is a bit larger as well. These are the two radiuses. This line and that one. And so same type of question. The only difference is the radiuses have changed. The radius and the other radius are different. Okay, what is the outer radius? This height, again, corresponds to the square root of x function. The other height is correspond to x. But the radius, the larger radius, is up to the x-axis. This distance is square root of x. Plus this extra 1 that will be give us the radius of the outer one. The outer radius is square root of x plus 1. The inner radius would be the height up to the x-axis plus this part, plus 1 again. It would be x plus 1. This would be the only difference between this question and the last one. The last one, the distance was from the x-axis, so we got x and square root of x. Now you have the distance from the line y equal to -1, which is going to give you the radius is x plus 1 and x plus square root of x plus 1. So what would the area? Area would be similarly pi square root of x plus 1, the outer radius squared, minus pi, the inner radius, x plus 1 squared. And again, you can simplify this area as a function of x. Say pi is common, factor out the other two terms. So if you square this two terms, you'll get, okay, let me write this again. Square root of x plus 1 squared minus x plus 1 squared. If you square these and subtract them from each other, what you get is negative x squared. I'm gonna skip some steps, minus x minus 2 square root of x. The other terms will cancel out. I think this is plus 2 square root of x. Okay, make sure that you double check my work, but I think this looks correct. So how do you find the volume? The volume would be integral from 0 to 1. These are the boundaries. Pi negative x squared minus x plus 2. Instead of x square root of x, I write x to the power 1/2 dx. And the integral would be pi negative x cubed over 3 minus x squared over 2 plus 2x to the power 1/2 would be 2 times x to the power 3/2 divided by 3/2. Evaluated from 0 to 1. If you replace 1, what you get is pi negative 1/3 minus 1/2 plus 4/3. If you replace 0, you'll get 0, so minus 0. So therefore, the volume turns out to be pi times negative 1/2 minus, that is 1 minus 1/2, so pi over 2. You can notice that the volume here is pi half, and in the last example, in the first section, it was pi over 6. And by increasing the radius, the volume became larger because the rotation becomes bigger, so therefore each area becomes larger. Okay, you double check my work, but I think this is correct. I don't see any problem with this. Here's another, these are examples that we did this by rotation. Here's another example of a pyramid. When given with a square base and a length L, the base has length L and the height is given H. And they ask you to figure out this, the volume created by this pyramid. Let me draw this actually vertically so you can see it. This is the base of the pyramid, and kind of looks like this. But instead of looking at it vertically, I put it sideways on the x-axis. This way, it's easier. So this length is basically given L, and the height up to the center is given H. So this H is the height from the top to the center. And if you put it on the side, this is basically at the bottom, this length. So the upper half has length L half. So here, if I cut through this and you look at half of this, if you focus on this triangle, it's basically the same as looking at this height, that length, and this. We're basically looking at this triangle. Why am I looking at this triangle? I just want to figure out this area of this red section, because if we assume x is here, then basically we need to figure out what is a of x. Okay, so let's look at this triangle. This is x. The whole length is given h. The height here is half of the base, which is L over 2. And we need to figure out what is this height. Let's call it question mark. So we just need to figure out what is this height, question mark. One of the properties of similar triangle, if you look at the smaller triangle, compare with the larger one, question mark, x, h, and L over 2. The ratio is always a fixed number. So question mark divided by x equals to L over 2 divided by h. This is one of the properties of the similar triangle. So what is the question mark? Therefore, the question mark is multiply both sides by x. X times L over 2 divided by h. So I figured out this height. The question mark is basically x times L divided by 2h. Why did I need it? If you look at this red section, that red section is basically a square. This is basically a square. Again, if you look at through the bottom or through this direction, you'll notice that that would be a square. And what we found is half of it is that question mark. So basically the length of that square is x times L divided by 2h multiplied by 2, because we found half of it. So if you multiply by 2, the 2's will cancel out. So this area of each square could be calculated as x times L divided by h squared. Length times width is the same in this case. So you get x times L divided by h. You can rewrite this as L squared divided by h squared times x squared. Why did I write it this way? Is because L and h are constant. These are fixed values. X is only variable. So we want to find the volume. What would be the volume? Let me change this back to green. So the volume would be the integral from 0 to 1 L squared divided by h squared times x squared dx. L and h are constant, so I can consider them to be constant. The antiderivative of x squared is x cubed over 3. Evaluated, not from 0 to 1. What are the boundaries? It starts from 0 up to h. The x changes from 0 to h, not 0 to 1. 0 to h. 0 to h. And now instead of x, replace h. You'll get L squared divided by h squared times h cubed over 3. If you replace 0, you'll get 0. And if you simplify that, that is 1/3 L squared h. And this is the volume of that pyramid with a square base L and a height h. Okay, this is basically it for this section. Next time we will discuss more of a volume created by rotation, cylindrical volume, and stuff like that. So I'm going to stop at this point.